Good evening, students. Myself, Dr. Divya Gildial, in continuation with my lecture series for diffraction syllabus, which is being covered under the AKTU scheme. Now, I will tell you about diffraction grating. Now, the grating word is new to you. So, first understand what is meant by the term grating. Grating is basically, you studied in diffraction single slit, then you studied double slit. Now you are studying n number of slits. So when a plain glass plate is taken and large number of lines are ruled on this with the help of a diamond pencil, then this setup is known as grating. It consists of n number of slits and n number of opaque space. So your syllabus was single slit 1, double slit 2, and now n number of slits. So when n number of slits are there, they will give you n number of spectrals. So now we are studying grating today. So look at the diagram here in front of you. This diagram due to diffraction has come because of n number of slits. See, this has diffraction grating consists of large number of parallel slits of equal width separated from one another by equal opaque spaces. Slit width plus opaque space is equal to grating element. Here, slit width S1, S2, S3, etc. are slit widths, and distance between them is the opaque space. So E plus D, slit width plus opaque space, is the grating element. Ray of light is falling on these slits, lens is converging them, and you are getting a diffraction pattern on the screen. You can see in this pattern, it is followed central maxima, followed by secondary maxima and minima. So diffraction grating is constructed by ruling large number of parallel and equidistant lines on a plain glass plate with the help of diamond pencil. Usually the ones used in the laboratory have lines like 12,800, 15,000, 10,000 lines per inch. Okay, now this setup can be compared to n number of slits. So this setup, let E be the slit width, D be the separation between consecutive slits, then E plus D will be known as the grating element. And we have studied that resultant due to single wave of amplitude capital A equal to NA is given by R equal to A sine alpha upon alpha. Now path difference between S1, S2, S2, S3 till Sn here. S1, S2, the perpendicular dropped here. This is the path difference. S2, S3, perpendicular dropped here. This is the path difference. So we take the resultant of these path differences, and phase difference comes equal to 2 pi by lambda into E plus D sine theta, where beta again we have assumed as this constant expression. Resultant intensity will be given by R2 sine n beta by 2 divided by sine 2 beta by 2. R dash is R sine 2n beta by 2 divided by sine beta. So instead of R, and we have written A sine alpha by alpha here. R, the resultant intensity, A sine alpha by alpha. So we have put R here and A sine n beta by sine beta. Now have a very closer look at this expression. Resultant intensity due to n number of slits is given by intensity due to single slit, A sine alpha by alpha square, this is R and this is I square, due to N slit. Sine square N beta by sine square beta. So the factor A square sine square alpha square gives the intensity pattern due to single slit. The factor sine square N beta by sine square beta gives distribution of intensity due to interference from all the N number of slits. So with this intensity expression, we can find the cases of maxima and minima. This is what we are now going to do. We will find the condition for principal maxima. Intensity will be maximum when sine beta equal to 0 or beta equal to plus minus n pi. So taking limit beta tending to plus minus n pi, sine n beta by beta. We have just taken the limit of this expression, d by d theta of sine theta is cos theta, putting this value and taking the limit, we get E plus D sine theta equal to plus minus n lambda. So this gives us the direction of the various first, second, third order principal maxima and minima. Secondary maxima, we will differentiate the intensity expression like we did in the double slit equation, and on differentiating the same with numerator denominator formula, we get the intensity of secondary maxima is to intensity of principal maxima equal to 1 upon 1 plus n square minus 1 into sine square beta. So it is clear that when n increases, the intensity of secondary maxima decreases. Here is your spectral distribution due to n number of slits or due to grating. There, here the zero order principal maxima followed by secondary maxima and minima. Formation of spectra with grating, E plus D sine theta equal to plus minus n lambda. Now, condition for absent spectra in grating. At times, what happens is that certain colors are not observable in a grating. So how to find out that condition? Direction of principal maxima due to grating is given by E plus D sine theta equal to n lambda, where n is order of principal maxima. Direction of maxima due to single slit will be given by E sine theta m lambda, where m is 0, 1, 2, 3. Single slit, we have not taken the opaque space, that is 0. So it becomes E sine theta m lambda. Now we divide equation 1 by equation 2. We get n is equal to E plus D by E into m. Maximum number of orders that are possible in a grating. E plus D sine theta is n lambda. So n is E plus D sine theta by lambda. So maximum possible value of theta sine 90 is 1. So n maxima is E plus D by lambda. If number of lines per inch is written on a grating, then the grating element is given by E plus D equal to 2.54 by n, and the condition where n equal to E plus D by E into m is satisfied, that order of spectra will be missing in the grating spectra, wherever this value becomes equal to this. The difference between grating spectra and prism spectra: grating spectra is formed due to diffraction. Prism spectra is formed due to dispersion. Grating gives large number of spectras. Prism shows one and only one spectra. The spectra of grating is less bright. The spectra of prism is more bright. Spectral lines in grating are straight. Spectral line in prism are slightly curved. This question is asked in section A. Dispersive power in any optical apparatus, be it prism, be it grating, be it a plain glass plate or anything, the dispersive power of a diffraction grating or any optical apparatus is defined as the rate of change, in this case of diffraction, as angle of diffraction with change in wavelength. D theta upon d lambda is known as dispersive power, and very easily we can find an expression. See, the grating equation for plane transmission grating for normal incidence is E plus D sine theta equal to n lambda. Here E plus D is the grating element, theta is angle of diffraction. So differentiating this equation with respect to lambda, because we need d theta by d lambda. D theta by d lambda is the dispersive power. We get E plus D, sine theta differentiated becomes cos theta, and d theta by d lambda, lambda this side is, so it becomes reduces to n. So d theta by d lambda is equal to n upon E plus D into cos theta. We can simplify or write this expression in various other forms because numerical is asked on this expression. So using cos square theta plus sine square theta equal to 1, we have written cos theta equal to under root 1 minus sine square theta. So putting sine theta equal to n lambda upon E plus D. Where did we get this from? Here. E plus D sine theta is equal to n lambda. We get d theta by d lambda is equal to n upon E plus D into under root 1 minus n lambda upon E plus D square, or d theta by d lambda dispersive power is equal to 1 upon under root E plus D divided by n square minus lambda square. So dispersive power is directly proportional to the order of the spectrum, inversely proportional to the grating element E plus D, and inversely proportional to cos theta. A very simple numerical we will discuss. In grating spectrum, which spectral line in fourth order will overlap with third order line of 5461 angstrom? See, any numerical on grating comes, the formula to be used is E plus D sine theta equal to n lambda. What have we been given in the question? We have been given that a parallel beam of monochromatic light is allowed to be incident normally on a plane diffraction grating having 5,000 lines per centimeter. The second order spectral line is observed to be deviated through 30 degrees. Calculate the wavelength. So E plus D is equal to 1 upon 1,000, 5,000 lines per centimeter, theta equal to 30 degree, and n equal to 2. So lambda is equal to E plus D into sine theta by n. Putting the numerical values, we get 5,000 angstrom as our answer. In a plane transmission grating, the angle of diffraction for second order principal maximum for wavelength 5,000 angstrom is 30 degree. Calculate the number of lines in 1 centimeter of the grating. Again, E plus D sine theta equal to n lambda. For second order, n equal to 2. Theta has been given as 30 degree. Lambda is 5,000 angstrom. We change it into centimeter. put these numerical values here and we get the answer. Resolving power of optical instruments, the ability of any optical instrument to form separate images of two nearby objects is known as its resolving power. Look at this diagram here. A and B are clearly resolved. Here, A and B are just resolved. And in this diagram, A and B are not resolved. Thank you. क्या कह रहा है